This is differential equations section 2.6. In this video, we're going to go over 4 special examples and how we can use substitution to solve these unique cases. So an equation dy dx equals f is homogeneous if the right-hand side can be written as a function of y over x. We're going to jump straight into an example to explain this. So consider dy dx is equal to y squared minus xy plus x squared divided by x squared. This equation does not appear to be homogeneous at first glance. However, it can be written as a function of y over x. So we'll go over that simplification here. We'll separate it into a sum of 3 pieces. And then we will cancel out whatever we can. So here we're going to lose an x. Here this is just going to become 1. And importantly, in the first one, we notice that y squared over x squared is just y over x all squared. And we do in the end get into a form where everything is written in terms of y over x. So if we perform a substitution where we let v equal y over x, we can write dy dx in terms of a single variable. And we call this equation dy dx is equal to g of v, some function of v. Now, if v is equal to y over x, that means that y is equal to v times x. And if we want to get what dy dx is equal to, so we can do a substitution, well, that's actually going to be a product rule on the right-hand side. So v times the derivative of x is just v, but x times the derivative of v is x dv dx. So gv is equal to v plus x dv dx. Why is that? Well, if we scroll back up, we see that gv is equal to dy dx, and dy dx is equal to v plus x dv dx. So using substitution, g of v is equal to v plus x dv dx. Now this equation is actually separable. So let's get all of our v's on one side and all our x's on the other. We start by just subtracting v from both sides. Then we're going to move the x's to the left and the v's to the right. And then we integrate. Left-hand side, simple enough, that turns into ln x. The right-hand side, we have to find the integral of 1 over gv minus v. Let's do an example. Solve dy dx is equal to y over x squared plus y over x. Now, this is clearly homogeneous. We don't need to actually simplify this like we did with the previous one. So we get that g of v is equal to v squared plus v, because y over x is v. So we get v squared plus v. Now, as we showed before, since v is equal to y over x, that means y is equal to vx. And we get that dy dx is actually equal to v plus x dv dx. So we can perform a substitution to now say that these two values are equal to each other. So v squared plus v is equal to v plus x dv dx. Now, if we look back, we can get the x's to the left and the v's to the right, using a separable, using the steps for solving some separable equations. So we get the ln x on the left, but what do we have on the right? Well, what is 1 over gv minus v? Well, g of v is equal to v squared plus v. We want to subtract v from that to get our denominator. So that's just v squared. So our denominator is v squared. So on the right, we're just integrating 1 over v squared. Now the integral of 1 over v squared using our power rule v to the negative 2. We're going to increase that negative 2 and then divide. So it becomes v to the negative 1 divided by negative 1, which is equal to negative v to the negative 1. And that's how we get that integral. Now, our goal is to isolate v. So we multiply both sides, or sorry, we just take the inverse of both sides, really. We'll make this correction right now. This should actually be 1 over ln x plus c, all in the denominator, because all we're doing is taking the inverse of both sides and moving the negative sign over. So we'll carry that through as we perform this substitution, that v is equal to y over x, but the right-hand side should instead be negative 1 over 1x plus c. And then multiplying both sides by x, we should get negative x over ln x plus c. But on the left-hand side, we have managed to isolate y, so we have an explicit solution. Now, we need to be careful about our additional solutions. X equals 0 is an additional solution here. Clearly, x equals 0 cannot actually be a solution to the initial value, to the initial problem, though, because y over x does not exist when x equals 0. Now we're going to look at our next type of examples. dy dx is equal to some function g of the variables ax plus by. So it's actually a single variable, and we're going to call that variable ax plus by. So just like in the previous example, we're looking for a way to turn a multivariable function into something in terms of a single variable. Now we're going to do a substitution as before. We're going to let z equal ax plus by. So let's see how this type goes. Suppose dy dx is equal to vx squared plus 12xy plus 9y squared plus 1. Now, this is not clear that 4x squared plus 12xy plus 9y squared plus 1 is equal to some function g of ax plus by. So we're going to have to do some factoring here. 4x squared plus 12xy plus 9 squared is actually equal to 2x plus 3y squared, and then don't forget the plus 1. Now, this actually is a function of g of ax plus by, where a is equal to 2 and b is equal to 3. So we're going to perform our substitution. Z is equal to 2x plus 3y. In which case we now have that dy dx is equal to z squared plus 1. Well, what is dz dx equal to? We're just going to take the derivative of both sides of this equation with respect to x. We get that dz dx is equal to 2 plus 3 dy dx. Now, we're going to stop here because I want to explain why we're doing all these things, because some of these steps may not be very intuitive. The reason we did this is because we need to solve for dy dx because it is in the original equation, and we're going to need to perform a substitution. So in order to get from z equals 2x plus 3y to something that has a dy dx in it, we would need to take the derivative of both sides with respect to x. So that's why we've moved to this step. And then we isolate the dy dx term. And we get that dy dx is equal to 1 over 3 dz dx minus 2. And then we finally do our substitution. From up here, you can see that dy dx is equal to the z squared plus 1. And dy dx is also equal to 1 over 3 dz dx minus 2. We're going to do the substitution and set these two expressions equal to each other. Now, this, believe it or not, is separable. We've just got to do a little bit of work to get things in the right spot. So let's multiply both sides by 3 and then add 2 to both sides to isolate this dz dx. And now it becomes more apparent, once you simplify on the right, that we can move all the z's to the left and all the x's to the right. And we're going to use our steps for separable equations. So we're going to take the integral of both sides. Now the integral of the right-hand side is simple enough. The integral of 1 is just x plus c. But now we need to work with the left. When we see 1 over something squared plus a constant, this should remind us of arctan. So that's what we're going to try to build towards. So the first step is to make this 5 look like a 1, because the original equation has a 1 in it. So we need to factor out 1 over 5, and the 5 does begin, it starts to look like what it needs to look like. But this 3z squared is now 3 over 5z squared. In order to make that some variable squared, we need to take the square root. So this becomes the square root of 3 over 5z all squared. Now, as ugly as that may seem, it is now finally some variable squared plus 1. We're going to perform a substitution, just calling it u. And when you do a substitution in integration, you take the derivative of both sides, and then you isolate the dz term so that we have something to substitute back in. And now look what we've accomplished. We have gone from this thing, which was rather ugly, through a substitution. It is now just some variable u squared. This denominator, square root 3 over 5, it's just a constant, so we just bring it outside of the integral. So everything that's inside the integral looks much simpler now, and we can actually integrate. The integral of 1 over u squared plus 1, as we stated, is arctan of u. Then we plug back in what u is equal to. U is equal to the square root of 3 over 5 times z. Multiply both sides by this denominator because we want to isolate this z term to move toward an explicit solution. Now, arctan, that can be removed by taking its inverse function of both sides, which is tan. So if we take tan of both sides, the arctan goes away, and we're now taking the tangent of the right side. And then we're just going to divide both sides by root 3 over 5 instead of multiplying by root 3 over 5. We'll do a quick explainer on that. If you divide something by the square root of 3 over 5, remember that that's equal to the square root of 3 over the square root of 5. And it's like multiplying it by the reciprocal. So root 5 over root 3 is what we're going to multiply both sides by. That eliminates the factor on the left, and it gives us a new root 5 over 3 factor on the right. Now we're going to simplify a little bit. 5 root 3 over 5 can simplify, and we'll explain that. 5 times root 3 over 5. Remember, that's root 3 over root 5. But also note that 5 is equal to the square root of 5 squared. So we can cancel out that root 5 in the denominator with one of these root 5s in the numerator. And we're left with root 5 times root 3, which is just equal to the square root of 15. So that's how we perform this simplification. Now we're going to do a substitution. Z is, the way we defined it, equal to 2x plus 3y. We're going to go all the way back to remember that. Right here. We've accomplished everything we need to by using z to get into a separable state, separating. Now we need to put it back in terms of x's and y's so that we can solve explicitly for y, which is simple enough because now that we have 2x plus 3y on the left, we can just subtract 2x from both sides of the equation and divide by 3. And we now have the y isolated. So this is an explicit solution, and we only have x's on the right. So we're done. One other thing I'll note is where this d came from. When I multiplied through these brackets, 15 times x became 15x, but 15 times c, well, we just gave that a new name. That's just d. And that's how we reach our explicit solution. Okay, our third example are Bernoulli equations. These are first order equations that can be written in the form dy dx plus some function of x times y is equal to some function of x times y to the n, where p and q are continuous on some interval and n is any real number. Now, if n is equal to 0 or 1, previous methods can solve equations of this form. Otherwise, we will use a substitution. V is equal to y to the 1 minus n. And this is going to be very similar to what we've been doing up to this point, where we are performing a substitution to eliminate some of the variables and rewrite the equation in terms of other variables so that the equation takes a form that we're more familiar with. So if we have dy dx plus some function of x times y is equal to some function of x times y to the n, let's divide through by y to the n. So every term divided by y to the n. So the y to the n here disappears. Y over y to the n becomes y to the 1 minus n. And we divide by y to the n here as well. Then we perform our substitution. Now, just as before, as soon as we perform our substitution, we're going to take a derivative of both sides with respect to x, because we're going to need a dy dx term. Because we're not going to be able to substitute into the main equation unless we know what it is in terms of dy dx. Now, we'll just move that 1 minus n over to the left. The reason we do this, we've actually accomplished something here. Y to the negative n dy dx on the right is in the equation we're dealing with. So we can perform this substitution entirely, taking out y to the negative n dy dx and replacing it with 1 over 1 minus n dv dx. And that is exactly what we've done here. So take a moment to see how this equation is the same as this equation when you use this substitution. Particularly note that we are now writing this as v, whereas before we wrote it as y to the 1 minus n, and that's using our substitution. Now this equation is linear. It has some constant times dv dx plus some function of x times v is equal to some function of x. So again, we have accomplished our goal, taking something unique that we didn't really know how to work with, changing out one of the variables for another, and reaching a form that we're more used to. So if you think back to section 2.3, you'll remember how we solve linear. And we'll do an example to remind ourselves. Solve dy dx plus 2y is equal to 3xy cubed. Remember that the first step was to divide through by that y cubed. So let's go back up just for a moment to remind ourselves. This y cubed term is the y to the n that makes this a Bernoulli equation. We're going to divide through by y cubed every term. So we get y to the negative 3 here, y over y cubed becomes y to the negative 2, and the y cubed term just disappears here. Now we do our substitution. V is equal to y to the negative 2. Then we get negative 1/2 dv dx plus 2v is equal to 3x. Now that's skipping a few steps from what we did before, but since we already did those steps, we don't need to do it every time. So I'll just move back here. We're jumping all the way from, I got to do some erasing. We're jumping all the way from this step to this step. So if you're trying to follow along, we know these things are true, so we don't need to prove them every time. And we're going to jump down to the simplified form at the bottom. So that's what we're seeing right here. Negative 1/2 dv dx plus 2v is equal to 3x. And this is linear. We've got function of x times dv dx plus function of x times v is equal to function of x. We're going to multiply both sides by -2 just to clean things up a little bit. And now our integrating factor, if you'll recall from section 2.3, is e to the power of the integral of this p of x term, the thing multiplied by v. So we're going to multiply through by e to the power of the integral of -4. Now, we don't need that integration sign to hang around too long because we know the integral of -4 is -4x. So we've multiplied through by e to the -4x everywhere. Actually, negative e to the -4x. Oh, sorry, it is positive e to the -4x. These negative signs were already here. Sorry to confuse. The integral of -4 dx is equal to e to the -4x. And that's what we've multiplied through. So if you'll recall from section 2.3, the reason we do this is to make the left-hand side look like the result of a product rule. And now that it's taken that form, we know that the left-hand side is actually the derivative of e to the -4x times v. So we can write it as such. The right-hand side, we don't do anything to right yet. But now we're going to take the integral of both sides. Now, if you take the integral of a derivative, they just cancel out. And we're left with v e to the -4x. On the right-hand side, well, we can factor out the -6. But now we're left with the integral of x e to the -4x dx. You may recognize this as an integration by parts problem. Not a very difficult one, though. We're only going to need to do integration by parts once, where we're going to be taking the derivative of x and the integral of e to the -4x. So here we let u equal x, and we take that derivative, which is just dx. Over here, we let dv equal e to the -4x. When we integrate that, we get -1/4 e to the -4x. And now we plug it into our integration by parts. So if you recall, this is uv minus integral of v du. If you're unfamiliar with integration by parts, you can go back perhaps to your calculus textbook and refresh yourself on that. But now u times v is x times -1/4 e to the -4x. That's how we're getting this term. And the integral of v du is the integral of -1/4 e to the -4x times dx. Now that integral is easy enough to solve for. But first, we're going to be very careful about our negatives. Because if you'll notice, there are really just negatives everywhere here. We got a negative here, negative here, negative here, negative here. So we're going to be very careful to make sure we don't mess these up and multiply them together to make positives. So these two negatives make a positive. And then these two negatives multiply to make a positive. And I've made a mistake because that's not what happens. So let's be more careful this time. The reason I've broken this into 2 steps is because this negative right here is multiplied through the entire set of brackets, whereas these negatives inside the brackets only affect each other. So we do start by multiplying this negative by this negative and getting a positive. That is true. But now what I need to do is carry this negative through every term in the brackets, making a positive here, but making a negative here. There. Now we've properly handled our negatives. Now we can integrate what 1/4 e to the negative 4x is. Well, when you integrate e to the negative 4x, it stays as e to the negative 4x, but you have to divide using your chain rule by this value. So we end up dividing by -4. So this negative becomes a positive, and this 1/4 becomes 1/16. Now, lucky for us, there is an e to the negative 4x term that is just going to cancel out everywhere. We're left with v is equal to 3/2x plus 1/16. You may be wondering where the 3/2 came from. That is just this 6 divided by 4. Now, if we go all the way back to the beginning, v is equal to y to the -2. And we've now got this written in terms of y on the left, x is on the right. We've gotten rid of all the v's. This is an implicit solution, but we think we can get an explicit solution. So remember that y to the -2 is equal to 1/y to the 2. So we're going to want to take the inverse of both sides of this equation, but taking inverses is a lot nicer if you get a common denominator first. So we're going to get a common denominator on the right, and then we'll take the inverse to get our y squared on the left, which just gives us 16/24x plus 1 on the right. Finally, take plus or minus the square root, and you have an explicit solution. Okay, we have one more example we're going to do. But first off, note that if we had settled for the implicit solution with y to the -2 isolated, y equals 0 would have been eliminated as a possible solution because there would have been a y in the denominator. But remember that we cannot always do things as nicely as we just did and isolate y properly. So sometimes we do have to settle for an implicit solution. Okay, now we're going to look at equations with linear coefficients. So these are equations of the form a1x plus b1y plus c1 times dx plus a2x plus b2y plus c2 dy is equal to 0, where all of these ai's, bi's, and ci's are constants. Now you can read page 74 and 75 in your textbook to see some special cases of this form, but we're going to be interested in the general case that does not easily simplify. So we're going to assume b1 is not equal to a2, and a1 times b2 is not equal to b1 times a2. These are simple things that have different ways you can solve them, but we want to just avoid those so we can get the general solution here. We will attempt to find a substitution for x and y so as to eliminate c1 and c2. So we think there is something we can replace x and y with such that c1 and c2 are just going to cancel out. So we're going to let x equal u plus h and y equal v plus k, where h and k are constants. This can be tricky when we do substitution, so we need to be very clear. X is equal to u plus h. We're going to let u be a variable and h be a constant. And the same thing with v plus k. We're going to let v be a variable and k be a constant. So in the first step here, we're just doing the substitution, which of course just seems to make things uglier. And then we'll expand it, multiplying a1 by u and then by h, expanding the b's as well. Now, remember our goal. We wanted C1 and C2 to just disappear here. How on earth would that happen? Well, our new terms, A1H, B1K, Those are just constants times constants. So those are just numbers. We're hoping that A1H plus B1K plus C1 is equal to 0. So that in essence, all three of those terms will cancel out and we'll just be left with A1U plus B1V times dx. And we're going to hope for the same thing in the second equation, A2H plus B2K plus C2 equals 0. So that we're left with A2U plus B2V times dy. Now let's suppose we have succeeded and that has happened. Then we'll be left with a much simpler looking equation. We've lost those constant terms. Well, now we can move the entire dx business to the right. And we can divide both sides by dx to isolate dy dx on one side. Now, why would we do this? We can actually make this look like our homogeneous equations, the first example from today, where dy dx can actually be written in terms of a single variable, and that variable is v over u. But there's one important thing to note here. We have dy dx is equal to something in terms of v over u, where we would need dv du is equal to something in terms of v over u. Well, remember that y is just equal to v plus some constant, and x is just equal to u plus some constant. So if you took the derivative of both sides of these equations, you would just get that y prime is equal to v prime and x prime is equal to u prime. So dy dx is equal to dv du. So that's how we reach this final homogeneous form. So let's see how this works. We're going to solve this linear coefficients problem. X plus 2y plus 3 times dx plus 3x plus 5y plus 6 dy is equal to 0. Well, remember what we want. We want A1H plus B1K plus C1 equals 0, and we want A2H plus B2K plus C2 equals 0. So that gives us the linear equations H plus 2K plus 3 and 3H plus 5K plus 6. So let's look at these equations. H plus 2K plus 3 equals 0, and 3H plus 5K plus 6 equals 0. Now you may recall this type of problem where we want to figure out what these variables are equal to. We're going to use, in the past, you would use either elimination or substitution. I think elimination will be fairly quick here. So we're going to multiply this equation by 3. That's going to give us 3H plus 6K plus 9 equals 0. And then we're going to subtract the other equation. The reason we do this, the h's now disappear. We get 6K minus 5K gets us 1K plus 3 equals 0. Gives us the K is equal to negative 3. Now, if K is equal to negative 3, we can plug that back into one of these original equations. And we get H plus 2 times negative 3 plus 3 equals 0. And that gives us that H is equal to 3. So H equals 3 and K equals negative 3. And those are the solutions we reached. Now we're going to plug those values into this equation. And again, it looks pretty messy. We've got X has been replaced with U plus 3. We've got Y has been replaced with V minus 3. But when you simplify and multiply everything out, the constants just fall apart. And we knew that to be true because we determined H and K specifically so that the constants would fall off. So we're just left with U plus 2V times dx plus 3U plus 5V dy is equal to 0. And we're left with dV du is equal to negative 1 plus 2 V over U over 3 plus 5 V over U. recall that dv du is equal to dy dx. So that's why we reach this conclusion. So this is homogeneous. So we're going to let z equal v over u. And we're going to do this problem as we would a problem at the very beginning of this video. So dv du is equal to negative of 1 plus 2z over 3 plus 5z. And we're going to remember that dv du is equal to z plus u dz du. Now, why is that? Well, z is equal to v over u. So, as we did at the beginning, since z is equal to v over u, we have that v is equal to uz, the derivative of both sides with respect to u gives us this product rule on the right. So now we have z plus u dz du on the left. We will isolate dz du. This is just finding a common denominator on the right and combining. Then this is a separable equation. So we're going to get the u's on the left, we're going to get the z's on the right, and we're going to integrate. Now the left is simple enough, that's just ln absolute u. But on the right, we have this fraction, 3 plus 5z over 5z squared plus 6z plus 1. This is going to require a substitution. We're going to let a equal 5z squared plus 6z. So the derivative of a is 10z plus 6. When we plug this back in, it's not immediately clear what we're going to accomplish, but you'll see that 6 plus 10z is double this numerator. We've taken the 2 and multiplied it by a and left the 3 plus 5z here, so they will cancel. And we're left with just the integral of 1 over a. So we get ln absolute u on the left is equal to negative 1/2, while the integral of 1 over a is just ln a plus c. Don't forget to put your constant in. Well, we substitute back what a is equal to. We set a equal to 5z squared plus 6z. And now we're going to set both as powers of e. So e to the ln u, that's just u. And then e to this whole thing. Remember, your exp function is equal to e to the power of. Well, e to the power of c can come out front as d, but we can actually keep simplifying here because we have e to the something times ln. Our laws of logarithms say that this factor, negative 1/2, can actually come out as a power. So we now have e to the power of ln, and they're just going to cancel out. So we get u is equal to d plus everything that was inside this ln, the absolute value of 5z squared plus 6z to the negative 1/2. And finally, u is equal to d over the square root of absolute 5z squared plus 6z. Now, it seems like we might have actually reached a solution, but we need y's and x's, not u's and z's. So we've got to unravel what we've done here. U is equal to this, but we know that z is actually v over u. But we know that v is actually y over 3, and that u is x minus 3. So this is actually our final implicit solution, and there does not seem to be any reasonable way to isolate y in this instance, so we are satisfied with that.